Hi everyone. Let's move on to the next topic, which is losses in a transformer. Okay, and so if we consider ideal transformer, so we don't find any losses in ideal transformer, but practically it is not possible. Losses in a transformer, so we have two types. One is core losses and another one is copper losses. So here we have two types of losses, and the losses which we get or which we find it in a core part of the transformer is called core losses, and similarly the loss which we find it in the winding part of the transformer is called copper losses. Okay, so there are two types of losses, copper losses and core losses. And so here core losses we also call it as iron loss. Iron losses. So since it can be made with the material iron, so this can also be called as iron losses, and similarly copper losses can also be called as winding losses, right? So core losses can also be called as iron losses, copper losses can also be called as winding losses. So in the first loss, that is core loss and in iron loss, so there exist two reasons for the energy loss in the core of the transformer. Okay, so one is hysteresis loss and another one is eddy current loss. Okay, so there are again two types of losses under the core loss or iron loss. So in the hysteresis loss, so what is this hysteresis loss? Hysteresis loss means when the alternating current flows through the winding. So here the magnetic core undergoes the cyclic process of magnetism and demagnetism. Due to this, there is a tendency of the flux density. So what is flux density? So here we denote it as B. So due to this, there is a tendency of the flux density B which lags behind the field strength H. Okay, so already you might have learnt about the concept called as a flux density and the field strength H and magnetic flux. So due to this, there is a tendency of the flux density which lags behind the field strength, that is magnetic field strength, which is H. So this tendency is nothing but hysteresis. So in a Greek word, hysteresis means lags behind. Okay, so here the B lags behind this H, so that is why we call it as hysteresis. So because of this, so we find a loss in a core part of the transformer, and this is called hysteresis loss, and hysteresis loss in terms of watts. So the loss whatever we define here, so whether it is hysteresis loss or eddy current loss, again the another type is winding loss, we express in terms of power. Okay, we express in terms of watts. So this hysteresis loss can be expressed in the form of, in terms of power, as, so this PH is equal to, so KH Bm to the power of n FV watts. And what are these variables here? So these variables are, so here we have KH. So KH is nothing but hysteresis coefficient, and of course it depends upon the material, what type of material we use it in the core part of the transformer. And similarly, so Bm. So what is Bm? Bm is nothing but maximum flux density, as we have already defined B as the flux density, is M indicating M is nothing but the maximum flux density. M is nothing but maximum, so Bm is maximum flux density in Tesla. The unit of the flux density is Tesla. And so next is N, where N is a constant and it varies from 1.5, which is greater than or equal to 1.5 and less than or equal to 2.5. And next is the frequency. Okay, what is the unit of frequency? So frequency in hertz, right? And next we have, so V. V is nothing but the volume of the core material. So volume of the core material, and the unit is again, so meter cube. So these are the variables you find it in the hysteresis loss when we express this in terms of the power. So next we have eddy current loss. So here the meaning of eddy is the circular movement. Okay, the meaning of eddy is circular movement. We know that ferromagnetic materials are good conductors, isn't it? So ferromagnetic materials are good conductors, therefore eddy current circulates within the core due to the alternating magnetic flux. So remember, so here the eddy current circulates within the core, so due to the alternating magnetic flux. So flux, and here, so and of course so this eddy current so may be quite high. Okay, so this may be quite high, and since the resistance of the iron is quite less or quite low, so here what happens, and which results in heating of the core, and the loss of power. So this is nothing but eddy current loss. Eddy current loss can be expressed in the form of watts, that is PE is equal to, so because we are expressing in terms of power, PE is equal to KE Bm square F square T square V. So already we have defined some of the variables here, so like KE, where KE is a constant one, and already we have defined B because it is a flux density, maximum flux density, and F is the frequency, and here already we have defined this V also because it is a volume of the core material, and the here, so another variable that we are going to define here is T. So where T is nothing but the thickness of the laminations, and since we have discussed how we can minimize the hysteresis loss, so we can also minimize the eddy current loss. How we can minimize the eddy current loss? That is by dividing the solid iron core, into the sheets. So remember, so eddy current loss can also be minimized by dividing the solid iron core, okay, into the sheets. So what do we call these sheets? We also call it as laminations. Remember, we also call it as laminations insulated from each other. So in this way eddy current loss can be minimized. And so now what is the total iron loss, or so core loss? So now the core loss, or so we define it as Pi, okay, iron loss. So the total iron loss can be defined as, or it is a summation of pH. So what is pH? Hysteresis loss plus eddy current loss Pe. So this is nothing but Pi is equal to pH plus Pe. Of course this is in terms of watts. So this is nothing but iron loss. Now what is the next loss? That is winding loss. Okay, so winding loss, or we also call it as copper loss. So in the next loss, that is in copper loss or in winding loss, here, so we know that the winding carries a current, okay, or the current passes through the winding. So how do we express the power? So power in terms of this I square into R, isn't it? So I square into R, and the power is wasted. So here the power is wasted, so because of the resistance which we use it at the primary as well as at the secondary, that is nothing but copper loss, okay. So the power is wasted, so because of the resistance what we use at the primary as well as at the secondary, and this copper loss depends on the magnitude of the current. Okay, the magnitude of the current which passes through these two resistances. So here, so the copper loss can be, so we can express it as PCU. So Cu indicates the copper loss. So this can be expressed as, now, so I1 square into R1 plus I2 square into R2. As I have already indicated, so power is wasted because of the resistance what we use at the primary as well as at the secondary. So of course it also, copper loss also depends on the magnitude of the current. So now copper loss, and if I consider I1 is equal to I2, okay, both the currents are same, so I can express it as, okay, instead of writing I1 I just express I2 square and R1 plus R2, okay, because I am taking I2 common. If I consider I1 as I2, so I have taken I2 common, and finally PCU is equal to, so I2 square into R, right. So R1 plus R2, what is R1 plus R2? Which is R equivalent. So R equivalent, and this can also be, since we have expressed this I2, since we have expressed this current in I2, so I'll just write it as R2E, okay. Why it is R2E? So that is, so since we have written this as 2, so here also I have written 2, and E indicates the equivalent resistance. This is nothing but copper loss, or we also call it as winding loss. And here, how do we express the total loss? Total loss in a transformer. So remember, the total loss is nothing but because, so we have discussed the loss in two different parts of the, that we occur at in two different parts of the transformer. So one is what? Which is iron loss, Pi, and another one is copper loss. So the total power, that is in terms of, so total power loss is equal to, it is a summation of the iron loss plus copper loss, and of course the unit is watts. So here, so far in this particular chapter, so we have discussed about the working principle of the transformer and different types of the transformer and different parts of the transformer, then EMF equation of a transformer, losses in a transformer, and the next topic is efficiency of a transformer. When there is a loss in a transformer, the efficiency of the transformer will go down. Okay, so or it comes down. So efficiency of the transformer will come down. So that means the output power. How do we find the efficiency of a transformer? So always we find efficiency of any system, okay, of any system can be calculated or can be analyzed with the help of the input power and the output power. Remember, when there is a loss, when there is a loss in a transformer, the output power always less than the input power. So remember, the output power will be less than input power. So then now what is output power? So of course in an ideal transformer, so we expect the output power will be almost equal to the input power, but since there is a loss in a transformer, so output power can be expressed as input power so minus some losses, right? So now what is a loss? So here, what is a losses in a transformer? So remember, here the total loss in a transformer, which consists of two different losses. One is iron loss and another one is copper loss. And so how do we express input power? So now power can be expressed as output power plus losses. Or I just represent it as P in, which is equal to P out plus P loss, right? Now how do we define efficiency of any system? So remember, efficiency will be always denoted by eta. So efficiency of a transformer is nothing but the ratio of what? Output power to input power. So now substitute equation. So here we know that this is output power, and let us call this equation as 1, right? And substitute equation 1 in efficiency equation. So what is P in? P in is equal to P naught plus P loss. Fine. So here in the next step we can write it as P naught divided by P naught plus, and what is P loss? P loss is nothing but, it is a summation of two different losses. So one we call it as iron loss, and which we represent it as Pi. Okay, so don't get confused with P in and Pi. Pi is a iron loss and P in is a input loss. Okay, so our input power, and Pi plus PCU. So now we have got the efficiency as P naught divided by P naught plus Pi plus PCU, and in the next step we can have it as efficiency is equal to, so what is P naught? P naught is nothing but, we know that, how do we express the power as VI cos phi, isn't it? VI cos phi. So divided by, what is this VI? VI are the parameters which we consider at the secondary part of that is secondary winding. Okay, so secondary winding. So now I can write it as V2 and I2. Why it is V2, I2? Because we are considering the output power. Output power can be measured always at the secondary winding. So V2, I2 cos phi 2, and similarly, so we have P naught over here. So similarly we write V2, I2 cos V2 I2 cos phi 2. I'll just write it as cos phi 2 plus, so we have Pi, which is iron loss, plus, so here, so we have PCU. So remember, here we are calculating for full load. Anyway, so I'll come back to this full load and fractional load later. So now we express efficiency as V2 I2 cos phi 2 divided by V2 I2 cos phi 2 plus, so Pi plus PCU full load. Okay, so PCU, again it is a copper loss, and here we measure it for full load. And here if we express efficiency in terms of percentage, then so we need to multiply this with 100. Now this is efficiency equation. So then what is this full load and what is the like half load or fractional load? So can, like, instead of having full load, so can't we have different loads? Of course we can have a different load, so we call it as fractional load. So fractional load, we express it as small n. Small n is nothing but the actual load, so divided by, it is full load. Right? Actual load means the load which we consider in a transformer. The load which we consider in a transformer is nothing but actual load, and so here the full load. This is, here n is expressed as the ratio of the actual load to the full load. So this is n, and here, so if the actual load is 1 by 2 and if the full load is, example, so I've just taken an example, if the actual one is half and the full load is 1, always the full load is 1, then so we can express it as, of course it is 1 by 2, or which we also get 0.5. So 1 by 2 is 0.5. Right? So in this way we express n as, so now what is n? Yes, n is nothing but fractional load. Okay, so with the help of fractional load, so can't we define the efficiency? So of course we can define the efficiency in terms of the fractional load. So eta, so remember this is n and this is eta. Eta in terms of percentage is equal to, so V2 I2 cos phi 2, so divided by, so which is n into V2 I2 cos phi 2 plus Pi plus n square into PCU. See, look at this equation here. Now look at this equation. So we have expressed same efficiency equation in terms of fractional load. So the equation which we have already defined is, this is for the full load. Okay, so now I'll just tell you, so what is the difference between the full load and fractional load. So in the equation, so we have n over here, so n into V2 I2 cos phi 2 divided by, again n into V2 I2 cos phi 2, because always we consider load at the output side. So n into V2 I2 cos phi 2 plus Pi plus n square into PCU. Okay, so why it is n square into PCU? And here, so if we consider the new I2, okay, so new I2, because, so what is PCU, which we can express it as I2 square into R2, isn't it? As we have already discussed, so PCU copper loss can be expressed as I2 square into R2, so R2E or R2. So here the new I2, that is for the fractional load, so this can be expressed as what? So n into I2, so I2 full load. Okay, so I2 is equal to n into I2 full load. And so if we just square this, so we get I2 square is equal to, so n into n square, so I2 square, so full load. Initially we have taken I2, so I2 is equal to n into I2, because with some load, so I2 this full load, and if we just square it, I2 square is equal to n square, I2 square full load, right? So what is PCU here? PCU is nothing but I2 square into R2. So here here in this case, if I just consider, so PCU is equal to n square into PCU. So what is PCU? So PCU is nothing but, so I2 square into this R2, which is equal to n square into, so what is PCU? So I2 square into, so of course this is nothing but full load, so I2 square into R2. So when R2 gets cancelled, so don't we get the same equation here? Right? So that is why I am just equating this equation. I am just equating this equation with, so PCU is equal to n square into PCU full load. So remember, PCU is equal to n square into PCU full load. So let us come to this equation, and we have expressed this equation in terms of the fractional load. So what is a fractional load? When n is equal to 0.5. So this we call it as half load. So when we get n as 0.5, we call it as half load. Similarly, we can have, so 0.25, and similarly we can also have 0.7. Any fraction we can have between 0 to 1. So here if I just consider n is equal to 1, okay, that is for the full load, because if you just substitute, the actual 1 is 1. So what happens is n 1 by 1 we get n is equal to 1. If we substitute n is equal to 1 here, so what happens? Efficiency eta is equal to, okay, so remember I am just substituting n is equal to 1. So this becomes eta is equal to V2I2 cos phi 2. So don't you get the same? V2I2 cos phi 2, so divided by, again n is equal to 1, V2I2 cos phi 2, so V2I2 cos phi 2 plus Pi, and if we substitute n is equal to 1, then we get PCU full load. That means PCU full load. So remember, this is this equation for the fractional load. So efficiency for the fractional load, and this is the equation for, so efficiency. This is the equation of what? So efficiency for the full load. So this is for the full load, and this equation for the fractional load. Fractional load. So if we substitute n is equal to 1 in the fractional load, then we get efficiency equation for the full load. So here we are going to consider the condition for maximum efficiency. Okay, so till now we have discussed about the equation that is efficiency of a transformer. So next we have the condition for a maximum efficiency. And here the transformer, so when the transformer works with the constant terminal voltage and with the, so constant frequency, of course the constant power factor, the efficiency. So here the efficiency varies based on the load current. So when the transformer works on the constant terminal voltage, frequency and the constant power factor, but still the efficiency so varies with respect to the load current. Of course the load current changes with respect to the load. And here, so in the transformer, so as you can see in this particular graph, so this is efficiency. So we have expressed it as eta, and another part is I2. So what is I2? I2 is nothing but the load current. Okay, as the load changes, it affects to the load current. So here, so as you can see in this particular graph, so as the load current increases, the efficiency also increases to certain point. Okay, as the load current increases, so remember the efficiency of the transformer so depends on the load current. So as the load current increases, even here the efficiency also increases to certain point, and once it reaches to some maximum point. So if the transformer is further loaded, okay, if the transformer is further loaded, so automatically the efficiency will come down. We have to find out what should be the condition for the maximum efficiency, because we need to get the maximum efficiency. Okay, so here eta max is the maximum efficiency, and so to this particular corresponding line, so you can observe this is the current, that is the load current which we have obtained for the maximum efficiency. And so here the condition to check or to have the condition for maximum efficiency, so we need to derive the efficiency equation with respect to I2. Okay, so with respect to I2 and equating this to 0. So let us call this equation as 1. Right, and before substituting eta, so we'll just again write so eta value. So what is eta? Eta is nothing but, so V2I2 cos phi 2, so divided by, so V2I2 cos phi 2 plus Pi plus, And so here actually, so we get PCU full load, okay, and we know that PCU can also be expressed in terms of current. So what is PCU? So as we have already defined, PCU is equal to I2 square into R2E, okay. So as we have already discussed the same equation in a copper loss. So PCU is equal to I2 square into R2E. So I am writing the same equation here. So since we are differentiating with respect to I2, so I am substituting PCU in terms of I2. So I2 square into R2E, right. So now we need to derive this expression with respect to I2. Now how can we differentiate this kind of equation? So we know that, so in differentiation you have already learned that, so du by dv is equal to u into v dash minus v into u dash divided by v square, okay. So now I am just simplifying eta equation here. So here we get, so differentiation of this with respect to I2. So what is eta? Eta is V2 I2 cos phi 2 so divided by V2 I2 cos phi 2 so plus Pi plus I2 square into R2E, and so this we are equating to 0, okay. Now let us call this equation as 2. So now we need to simplify this expression according to this function, okay, du by dv. How we can simplify this expression? So here I write it as, so V2 I2, I am just keeping the denominator part, that is V2 I2 cos phi 2 plus Pi plus I2 square into R2E. So now so I am just differentiating this term. So that is, so we need to differentiate V2 I2 cos phi 2, right, and then so minus, okay. I hope the next step is clear. So I have just written this part as it is, and so differentiating this V2 I2 cos phi 2, and similarly so minus, now I am keeping the second term as it is, so V2 I2 cos phi 2. Next, so differentiating with respect to I2, that is, so V2 I2 cos phi 2 plus Pi plus I2 square R2E, fine, and so divided by, so here we get this equation only at the numerator, so which is equal to, so what is denominator? That is v square, okay. So v square, so anyway, like since we are equating this whole equation to 0, I am just writing this part as denominator square, because anyway, so we are not going to simplify the denominator part because we are equating the whole expression to 0. So I have just directly taken the denominator part, that is v square. So that is in du by dv, so we had v square in the denominator, so directly I have taken the denominator square, so it is equating to 0. So since we are equating this to 0, so we don't get this term, and finally like in the next step, so we get only this term, okay. So here we have V2 I2 cos phi 2 plus Pi plus I2 square R2E. Now, so now we are differentiating with respect to I2. So if we differentiate this equation with respect to I2, then we get, okay, so this into what? V2 cos phi 2, because I2 becomes 1. So V2 cos phi 2, so minus, again, so minus here, so V2 I2 cos phi 2, and now so we are going to differentiate this expression with respect to I2. So into what? So into V2 cos phi 2, see the first term, we are differentiating the first term with respect to I2, so we get V2 cos phi 2, and since this part is constant, so we get 0 here, so plus, and this becomes what? So we have I2 square, so I2 square becomes 2 into I2 into R2E, isn't it? So remember here it should be in single step. So here I have taken minus, okay, and equating this to 0. So the denominator part is not there because we have equated the whole expression to 0. So here we get only this part. So we have simplified only this part as this and finally equating to 0. So further we need to simplify this expression. Okay, so now look at this equation. So I have written V2 I2 cos phi 2. So plus Pi plus I2 square into R2. So remember here, so we can write it as R2E or so only R2. So here we have V2 cos phi 2, so minus. So we have minus in this particular equation. So I have taken this term to right hand side. Okay, the second term to right hand side. So this becomes is equal to, so V2 I2 cos phi 2 into V2 cos phi 2 plus 2 into I2 R2. So now what happens? Look at this equation. So V2 and V2 gets cancelled. This cos phi 2 gets cancelled, isn't it? And so look at this equation. So we have only I2 over here. So multiply this I2 here. Multiply this I2 here. So what do we get? V2 I2 cos phi 2. Right? So don't you think this V2 I2 cos phi 2 and this V2 I2 cos phi 2 gets cancelled? Okay? Or if you are confused, so I will rewrite the expression. So V2 I2 cos phi 2 plus Pi plus I2 square R2 is equal to, so now I am multiplying this I2 here. So we get V2 I2 cos phi 2. Okay, so cos phi 2 plus, again multiply this I2 here. So we get 2 I2 square into R2. So what happens? V2 I2 cos phi 2 gets cancelled. So which part is left out here? What are the components? We get or left out Pi is equal to, or Pi plus I2 square into R2. So is equal to 2 into I2 square into R2. So we have I2 square into R2 is equal to I2 square into R2. So take this I2 square into R2 right hand side. So we get Pi is equal to, so 2 into I2 square into R2 minus I2 square into R2, we get only I2 square into R2. Right? So as I have already told you, we can write only R2 or R2E. So both are same. So now finally what we have obtained? Pi is equal to, so what is I2 square into R2E? I2 square into R2E is nothing but PCU, right? So this is for PCU. So now what is the condition for maximum efficiency or to obtain maximum efficiency? So remember the condition should be, okay, or the condition must be Pi is equal to PCU. So when do we get the maximum efficiency? When Pi is equal to PCU, okay. This is very, very important derivation. So finally we need to prove or we need to show that Pi is equal to PCU for that is the condition for maximum efficiency. Here we have proved iron loss is equal to copper loss, okay, for that is the condition for maximum efficiency. And with this condition, so we can also express the efficiency at maximum. So maximum, which is equal to, so we know that here V2 I2 cos phi 2, this equation is V2 I2 cos phi 2, so divided by V2 I2 cos phi 2 plus Pi plus, so PCU full load, okay. So this is only for the efficiency, and similarly to find the efficiency, that is maximum efficiency, so here now this equation can be written as, so V2 I2 cos phi 2, so divided by V2 I2 cos phi 2, and if I substitute PCU, so what should be the condition? Condition is Pi is equal to PCU. So if I just replace this PCU by Pi, then so we get Pi plus Pi, so this can be written as 2 into Pi. So in terms of percentage means it should be multiplied with 100. So what is this equation called? This is the equation of the maximum efficiency. So which is equal to V2 I2 cos phi 2 divided by V2 I2 cos phi 2 plus 2 Pi. So based on the condition, so we have defined the maximum efficiency. Thank you.